Vector calculus provides a powerful framework for understanding how physical fields change and flow through space. At its heart are core product rules that act as the primary tools for dismantling complex interactions between different types of fields, such as those involving scalar values like temperature and vector values like fluid velocity. These rules allow us to take an operation applied to a product and distribute it, revealing how each component contributes to the overall behavior of the system. The position vector, which represents a specific point in three-dimensional space, serves as a unique and simplifying anchor in these calculations. It possesses two fundamental properties that make it a constant baseline. It expands outward at a steady, uniform rate, meaning its total outflow or divergence is a constant value, and it possesses absolutely no inherent rotational tendency or curl. Because of these fixed traits, expressions involving the position vector often simplify dramatically, allowing more focus on the variables that actually change. This simplification leads directly to several vector null identities, which are mathematical vanishing acts, where complex-looking operations are proven to equal zero across an entire field. A prime example is the rotation of a gradient. Since a gradient always points in the direction of the steepest descent, it cannot, by definition, have any rotational flow. When these non-rotating gradients are combined with the naturally non-rotating position vector in specific cross products, the resulting divergence is also zero, providing a visual and mathematical proof of stability in the field. Finally, the decomposition of complex expressions allows us to see the individual ingredients that make up a physical phenomenon. For instance, the total outflow of a field can be broken down into a combination of the field's own expansion and the influence of its internal variations. More intricate operations, such as the rotation of a cross product, are revealed to be an additive mix of the field's curvature, its slope, and the way that slope changes along a specific path. By breaking these complex flows into simpler parts, like the intensity of a slope versus the product of a field and its own curvature, scientists can better model transport phenomena and other intricate physical behaviors.